Hello, thank you for joining this webinar. As Chris said, I'm Adam Parks. I'm the Technical Director for Flood Products at Jacobs. I've been in the industry over 20 years, and most of that time has been hands-on building models, undertaking modeling for a range of different projects in the UK and globally. So a lot of the stuff I'm going to show you today comes from my experience of hydraulic modeling and the challenges we face. So today I'm going to be showing you how new technologies, including Flood Platform, can be used to accelerate your delivery of hydraulic modeling projects, as well as touching on how we can optimize our models and the hardware we're using to run them to bring speed and cost efficiency, ultimately allowing us to deliver our projects faster. So in this presentation, I'm going to be covering a range of areas. First off, I'll have a look at some of the current and evolving challenges in hydraulic modeling, things that are causing us pain as users now and things that are likely to be causing us problems in the future. I will touch briefly on Flood Platform, one of our products, just to give you an overview of what that does. I'll also be looking at speed. So when we run these models, how can we speed them up? How can we accelerate delivery through use of optimized models and also use of cloud compute? I'll be touching on how to optimize your simulations, as well as the balance of cost and speed. So fastest isn't always best when it comes to cost efficiency. So I'll be having a look at that and what things you need to consider, particularly if you want to use cloud compute for simulations. First off, why are we doing this? What are the challenges, the issues which we're looking to address? So these in this presentation have fallen into two broad buckets. The first one is something I'm sure everyone's aware of, the ever expanding need for more simulations. Every project, every client, every strategy is looking to run more and more simulations to reflect how our technical capability has improved. We can model things we couldn't previously, as well as regulatory and scientific advances and requirements. How do we manage running those tens, hundreds, thousands of simulations? The other challenge is around better use of existing models and data. There's a huge back catalogue of data available to us. How do we get access to it? How do we make use of it? And what are the challenges around using that data? So thinking first about that requirement for more and more simulations. When I first started in the industry a couple of decades ago now, I was lucky in that most projects required me to run 10, 20 1D only simulations, which is something I could do quite happily on my local PC in the space of about an hour without any specialist hardware. Now we're looking at running hundreds, even thousands of simulations for projects. And the reason this has happened is multifaceted. Our software has become more capable. We're able to model things we simply couldn't model before. So we've moved from pure 1D models into 1D, 2D and pure 2D models. These are allowing us to model floodplain processes, complex hydraulics in more detail, and our clients are asking us for more detail and more confidence in these areas. There have been changes in the science, our understanding of hydrology, uncertainty around hydrology, joint probability, and so on has improved, and we've got more data we can throw at these things. And equally, we're being asked to do more by our clients to meet regulatory requirements. I'm often involved in FCRM, flood risk management projects, and we need to justify the benefits of our schemes. And so to do economic analysis, we're often having to run hundreds of simulations to generate the economic data we need to justify a scheme. This can be exploded out further if you've got complex sites with things like joint probability between multiple sources of flood risk, which increase the number of simulations required by an order of magnitude. Just to exemplify that, currently a simple mapping study, you can still get away with a few tens of simulations. So that'll be a few return periods, possibly a few different climate change epochs. That grows, you need to consider defenses and other issues. A simple appraisal can be a few hundred simulations. This is where we're having to do minimum, do nothing, do something for different epochs and different climate change horizons. We then move into the bigger appraisals. These are where you're spending hundreds of millions of pounds defending cities and large areas. It's not unusual for these to require in the order of a few thousand simulations, particularly where joint probability is an issue. And I've dealt with several of these projects over the years. We then move into the really big projects, the complex strategies. So the example we use is OxCam, which is the Oxford Cambridge Arc project. And that required some 45,000 simulations in order to assess the best way of managing flood risk on that large development area over a 100-year period. And then we've got sort of the one-off mega project. So we've been engaged by the Environment Agency to undertake the Thames Mapping Project. This is going to need in excess of 250,000 2D simulations in order to map the risk of breach all the way along the Thames. So there's a lot more pressure on us now to run more simulations, which makes it harder or impossible to run these locally with simple setups. We're now moving into the era we need more dedicated systems. The other challenge is around use of existing models. So there's a lot of data that's being produced. The Environment Agency alone in England have over 1,600 models in their available catalogue, which is all the green lines on the map to the right-hand side. If you factor in the models available in other countries, so England, Scotland, Northern Ireland, as well as held by the likes of utility companies, Canals and River Trust and other operators, there are thousands of models available. We want to make best use of these, but this is often a problem. A common scenario is you get hold of an existing model from, say, the Environment Agency, and you want to use it in a flood risk assessment. But when you get it, simulation data is missing. You may want to run 1 or 2 additional simulations for climate change. And this is a pain. It's harder than it should be. Key issues are sort of setting up those models, which are often referencing old file paths and running old solvers so you can reproduce the same results. So those are the 2 broad issues I'm looking at today and how Flood Platform and cloud compute can help. Before we get into how we run them, it's often worth looking at simulation optimization. We don't want to run more simulations or use more compute than we need to. There's actually a longer webinar on this tomorrow. So my colleagues in Jacobs are working with TUFLOW, BMT and the Australian Water School to give an hour-long webinar around simulation optimization. You can still sign up for it. There's a link there on our website. And it will be early in the morning UK time, but you can catch the recording, and that will be a really interesting presentation looking at all detailed issues around particularly TUFLOW optimization. I'm going to summarize that short now. So why do models take so long to run and what can we do about it? There are 2 broad areas here. So we can reduce the time it takes for an individual simulation to run, and we can reduce the total number of simulations we need to run. And we should be doing both. We should be challenging both. So the first thing we need to do is look at how we can speed up individual simulations. Some of that is common sense. The bigger the model, the bigger the 2D area, the longer that simulation will take. What can we do to cut that model size down to our area of interest? Can we reduce the model active area? Can we change the cell size of the models? And a key thing is the number of active and wet cells. That will really drive the duration of your model. Can we bring this down? Can we make decisions to reduce that? Another issue is the simulation duration. Do I need to run my model for 24 hours, 36 hours when the peak is at 4 hours? Can I reduce the duration of my simulation and therefore reduce the amount of computational effort? Model complexity is really important. So things like QuadTrue really help us optimize our cell sizes as well as subgrid sampling, but they bring their own challenges. We'll look in that webinar I mentioned with AWS tomorrow. Just subtle changes to the subgrid sampling, the SGS parameters within a TUFLOW model can make a huge impact on the duration of your model, but not make any difference to model quality. So we're looking for ways we can gain efficiency by reducing the computational effort to get the same result. Another thing that's often overlooked is model performance, model stability. If a model is inherently unstable because of some configuration or data quality issue, it will take longer to run. The time step will have to be lower to overcome that instability. So a key thing you can do is taking that one model, stress test it, understand, is it stable? Is there anything I can do to re-schematize it, to improve the setup that will speed that model up and allow it to run on a higher time step, therefore reducing the overall computational time. Once you've got your model humming, the other thing you need to challenge is the number of simulations. I looked at some examples where you're running tens, hundreds, thousands of simulations. It's really up to us to challenge our colleagues within our businesses, our clients, about how many simulations are really required. Every time you add another simulation, that's extra effort, that's extra compute. Do I need it? Is it going to add benefit to my project? And often you can reduce the number of simulations significantly just by being critical about what simulations are really required and reducing those to the bare minimum, therefore speeding up your project and saving your clients time and money. So you've got your models set up as efficiently as you can. You've narrowed down the number of simulations you need to the bare minimum. Now you're getting ready to run these things. Before we look at running options, both on-prem and in the cloud, I'm just going to recap quickly on what Flood Platform is, because this is the system I'm using to do this demonstration. So Flood Platform is a product released by Jacobs. It's been used within Jacobs now for about 15 years to manage all our hydraulic modeling work globally. And it's now available externally as a SaaS product. So this is a product based in the cloud you access through a web browser. And what it does is it gives you access, efficient access to cloud storage and compute. So underlying Flood Platform is Azure, Microsoft Cloud, and that gives you unlimited storage and a huge amount of compute, both CPU and GPU. And Flood Platform has been optimized for hydraulic modeling. So on top of that cloud and storage layer, we've got the functionality layer where we've got model management, visualization, security, collaboration, both internally and externally, as well as simulation and analysis. And that functionality could be accessed by you, the modeling teams, your clients, stakeholders, other team members. And I'll show you why this is an efficient way of delivering modeling simulations. Just to show you this looks like, and taking that example of an existing model, here's a model I built several years ago now, 15 years ago, for the Environment Agency, the Upper Mersey model. I've got a copy of that, I've requested it, and I've uploaded it to Flood Platform just by dropping it into the software. And what I want to do is run some simulation. So Flood Platform's uploaded that simulation, it's identified all the sims, and that some of them haven't been run. So the data pack I've received back is missing data. If I want to rerun those, I can do them one at a time. And I've got the option to choose the version of the solver I use. I don't, seconds of setup to do this. I can run them one at a time, or I can run them as batch simulations by choosing them and just dropping them into the run queue. So Flood Platform behind the scenes has sorted out all the file links. It's sorted out the versions of the solver for me. It's sorted out the licensing. And rather than taking several hours to disentangle this model, it can be done in a few minutes with Flood Platform. And once you've got your results, this is one that was run off platform, you can access the results. So you can see the data that's been produced, you can access the logs, so you can see the model performance, coming back again to that stability issue I mentioned earlier. And you can view the results all in a browser. So this makes it a lot easier for collaborating with your clients, with your stakeholders. So here you can see this is a pure 1D model. You can zoom right in, you can access the individual nodes, and you can access the results all within a web browser. And this takes minutes to do compared to hours to work through had you just received the files and had to work them out yourself. And this is just part of the functionality within Flood Modeler. There are plenty of other webinars and presentations looking in more detail at other aspects of Flood Platform. How fast? So you've got your model, it's all set up. How fast can you run it? And this is something that's changed dramatically in the last few years. So for this, I'm taking the TUFLOW benchmark data. So these are benchmark models you can download from the TUFLOW website and see how fast your own hardware runs. And we've got a range of models running from a few 100,000 cells through to best part of 12 million cells. And if you run those with a okay graphics card, you can see for the smaller models, they're running in less than an hour. For the bigger models, you're looking at several hours. And for the really big models, those 12 million cell models, it's taking over 50 hours to run some of these simulations. That's using a venerable old NVIDIA 1080 graphics card. These are great cards when they're released, but things have moved on. So if we do the same benchmarking with a 590, this is one of the best consumer cards you can get your hands on now. You can see those speeds really topple. For the really big models, you see the greatest benefit, 4 times faster running with a better card. you get less benefit for smaller models where the initialization time and the overall simulation time is still small. So you get reduced benefits for smaller models. It's really in really big, long-running models that the faster graphics cards bring a benefit. So you've got all these models, you want to run them through. It seems obvious you want to use the faster card. So that 1080 takes the best part of an hour to run a model, whereas the NVIDIA can take, the old 1080 card can take 56 hours to run a model, whereas the NVIDIA card, the 590, can take 13 hours. But it's worth looking at the price of these things. So you can pick up a 1080 now for about £80, whereas that 590 is going to cost you well over £2,500, and that's just the card. On top of that, you need a computer that can house it. These are big physical cards, and they need a lot of power to run them. So you're looking at several £1,000s additionally to be able to run these models. And when you think that the 590 card is 30 times the cost of the 1080, you start to wonder about that cost, speed, efficiency, that ratio of speed to cost. So let's have a look at that in a bit more detail. The first thing to say is we're moving towards the cloud. We can't possibly run all these simulations locally. And there are a lot of benefits to going to the cloud. You've got that scalability. You don't need to have hundreds of cards available locally to meet your peaks. You can scale into the cloud and scale your resources to your needs. It's resilient to power outages and disruption. So nothing more frustrating than setting your models off and coming back to find they failed because of a Microsoft update or something else has happened. With the cloud, you've got that resilience and that reassurance these things will carry on running. Also, the cloud helps reduce IT management time and produces a collaborative environment. You're not having to manage those internal resources, who jumps onto the shared machine and so on. There are cons, and the main one is the access to some types of cards you can have available. So you can't use some of those consumer cards in there. They are all commercial data center quality cards, which produces additional issues. Just to say, there is a difference between using the cloud, Azure, AWS, Google, versus using Flood Platform. So Flood Platform is based on Azure, but we do a lot of the setup for you. We manage all the cloud setup. Your compute instances are set up for you and pre-configured. We manage the containers for simulation, and we provide a full range of solvers and versions without you having to set anything up yourself. It's simply a matter of dropping your models in and pressing go, which saves a huge amount of time. We're offering in our cloud, we've got several GPU accelerators. We've got the T4, the A10, and the A100, and you can see these within the TUFLOW benchmarking to give you an indication of how fast they are. So the A100 cards are really great cards. They're on par with the fastest benchmark models in TUFLOW. The A10 are a bit slower, and then the T4s are slower still. And then this is going to come to cost versus speed. So we look again at these models ranging from a few 100,000 cells to, in this case, 3 million cells. I've taken off the 12 million one just so you can see the granularity of what's happening. As you'd expect, the A100 card is fastest, running that 3 million cell model in a little over 100 minutes, whereas the T4 is taking 4 times as long to run the same model. But we need to consider the cost benefit as well. So if we flip that and look at it in terms of cost to run, we see a different pattern. The A100 card is costing a few pounds to run that model, whereas the T4 is costing half that. The 3 million cell model is probably a bit of an extreme example. If we look down at the sort of million cell model, half-million cell model, you're talking somewhere around £1, sub £1 to run it on the T4, and a bit more than that to run it on the A100 card. So it's about identifying what's the sweet spot between speed and cost when we're running it, and we give you that capability. And I'll show you some examples in a second. Something else worth mentioning is that if you use Flood Platform to access the cloud, you have got preferential rates. So these show the costs of running these models, both the solid lines and the costs running them just using the list Azure price. If you just took out an Azure subscription, that's what we'd be paying to run these models. If you run it through Flood Platform, it costs you less. You can see there's something like £1 difference, those very large models with the A100. And the reason for that is we get preferential rates from Microsoft as Jacobs. We buy a lot of compute and storage. and therefore we can pass those reduced rates on to our customers. So you, as well as the saved time and effort in terms of setup, you're also saving money in terms of the cost of actually running your models through running it through Flood Platform. Just to give you an example of what that looks like. So for a fairly standard appraisal project, you may have 4 scenarios: do minimum, do nothing, 2 do somethings, 12 return periods to consider. So 1 in 100, 1 in 1,000, 5, 10, etc. And perhaps 3 climate change scenarios to consider. You work through all that, you're looking at running 144 simulations for that one project, which isn't an insubstantial number. It's not the huge numbers I looked at earlier for the big major projects, but it's quite a normal number of simulations to run. You've got a few options for how you do that. So if you ran it on your local hardware, you go off and buy yourself a shiny 590 card. That can run that model in about 73 minutes, not bad going. But you've got 144 of them to run. So that's going to take you 7 days to run all those simulations on a local machine, plus at least a day of setup costs. So you've got to set those simulations up, set up the machine, keep an eye on them, and check back on it. You're looking easily spending about £4,000 doing that for both the hardware cost and the setup time as well. You could choose to run it in Flood Platform, so using those T4s on Azure. The simulation time for an individual simulation is longer, so a couple 100 minutes, but because you can run them all in parallel, suddenly the actual program time shrinks dramatically. So you can run that in a day, and it will cost you a few £100 because all the hardware is dealt with on our side, all the setup time is dealt with on our side. If you need the results faster, you could opt for a faster card, so an A100, in which case the individual simulation time comes down closer to the sim time for the 590. But for the program, again, running these things in parallel, you can run the whole lot in 2 hours. They're faster cards, they're more expensive to run, therefore the overall cost increases, but it's not astronomical. So hopefully what this shows you is you've got flexibility now in how we run these very big models where you've got lots of simulations to look at. Just to wrap that up, and thank you for your interest. As I said, the computational demands of modeling continue to grow. We're being asked to run many, many more simulations than we were historically. We're also looking to make better use of existing models. So that poses its own specific challenges around how do I quickly and efficiently get hold of old models? How do I open them up? How do I rerun them? How do I find the right solvers? Before you run anything, careful planning and design of your simulations and your models can significantly reduce your compute needs. It's always going to be cheaper and faster to optimize your models and be rigorous in challenging the number of simulations than to just throw compute at it. And I'd always encourage that, no matter how you're doing it, on premise, in the cloud, using Flood Platform. Really challenge how you can deliver these models more efficiently. Increasingly, cloud resources allow us to scale up our compute, our storage to meet our project needs, especially where you've got tight deadlines. You can do these things in the cloud a lot faster than you can locally. But bear in mind, when it comes to choosing your hardware, both locally and in the cloud, fastest isn't always best when it comes to compute resources, particularly if you're cost sensitive. So you can often have models run slower and still cost you less than those super fast cards.